Hi, everybody. This is Brian Hepler with Quantum Formalism Academy, bringing you a crash course on topology and manifolds. It's one of our prerequisite courses for our upcoming course on Lie groups and their applications. This is a four-part lecture series where we'll be covering some of the topological foundations for the course. So these are things like general topology, smooth manifolds, tangent spaces, tangent bundles, and their applications to Lie groups or matrix groups. So in our first course, our first lecture, we will talk about introduction to topology. So this is a very quick run through of something like the highlights of a first course in topology, or maybe something like you might encounter in an analysis course. Um, Not too much on the general abstract topology. A lot of things focused on the context of subsets of some Euclidean space, um, with some general properties thrown in when it's necessary. So let's kick it off. So as a general outline for the lecture, we are going to cover some motivations, like what even is topology? Why do you care about it? And then go through some basic definitions, like a topological space and some of their sort of primordial components, like open sets, closed sets, continuity. Um, then we'll move on to homomorphisms and topological equivalence. So once you start doing some more math in any given subject, you always see, you talk about the objects, and the next thing is how they're related, and when are two of these things the same. So we'll see that homomorphisms will be our notion of when two topological spaces are the same. And then finally, we'll end with some key topological properties. So these are some things that are sort of invariant under homeomorphism. We think about these things as true invariants of these spaces, like compactness and connectedness, and a few others that are useful for our discussion on manifolds later on. So before we talk about what is topology, this is a silly joke that when you're talking about this subject with your friends or people who aren't in math, they've heard about geometry, they may have heard about algebra, probably haven't heard about topology. So I really liked this little display. Um, yeah, that's about like the common knowledge of the subject, the study of adding tasty toppings. We won't really touch on this thing, but I don't know, I'll have to include it. So more specifically, what is topology? We can think about it as it's the study of properties that are preserved under continuous deformations of a space. We haven't really defined continuity specifically in this case, but you could think about it intuitively as stretching something without tearing it, like an infinitely stretchy rubber sheet. Um, right. It's also more generally, more intuitively, like the appropriate setting to talk about continuous properties of a space. So no topology lecture will be complete without this sort of canonical joke. Um, why does a topologist consider a coffee cup and a donut to be the same? Or we'll see later how this will be replaced with homeomorphic. Well, it's because you can sort of continuously stretch a coffee cup into a donut. You flatten the part that contains the coffee, and you just have the little loop for the handle. And these are the same space as far as we're concerned. Now, why is this abstraction relevant? Well, there's a lot of different things. It's something you'll see depending on how you progress through mathematics. You might encounter it through different lenses. So someone who goes through and does maybe an advanced calculus course or a real analysis course for single variable calculus. So that's sort of when you're building up single variable calculus axiomatically. Um, you see maybe a little bit of general topology in the sense of metric spaces as a more precise way of handling differentiability, continuity, and so on. For us, coming from maybe like a linear algebra or an algebraic perspective, especially gearing toward things like Lie groups, we're going to be focused on a lot of matrix group examples throughout this. So you'll see like a lot of our examples are GLN, general linear group, or orthogonal groups or unitary groups and things like this. So one fun kind of application of topology is that we sort of get for free or very easily that the set of all invertible matrices are in fact dense in all square matrices. So you can think about any arbitrary square matrix can be approximated arbitrarily well by an invertible matrix. This is very useful for some applications. And then some things like compactness, which we saw on our last slide as a kind of a key topological property. This is a way of kind of ensuring boundedness of behavior. Your kind of analysis can't escape off into infinity, and you have to worry about less sort of divergent sums with when you have compactness in the arena. So our key goals for today throughout this lecture are to talk about some basic definitions, kind of build up a mental cheat sheet for the things we're going to see in upcoming lectures. So we'll talk about topological spaces. These are our kind of abstract building blocks, and open and closed sets, which are the fundamental like object within a topological space. Continuity, which is the key property of functions between topological spaces, and then homeomorphisms, which are our notion of equivalence of topological spaces. And then some key properties like compactness and connectedness, which we haven't talked about connectedness yet. And another one called Hausdorffness.